All right. Okay. So thank you for having me here. My name is Anto Joseph. I will talk about symbolic execution. Just to get a brief idea, how many of you have tried something related to symbolic execution? All right. Okay. That's some folks. Okay. Before I start with the world presentation, I would like to play a video of my hometown. I'm coming from India. So we do have a security conference in India in a place called Goa. So I invite you to submit to the CFP and have a look at how the place looks like. Okay, the volume should work. Is the volume?
The most fascinating water world on Earth, the Great Backwaters, Kerala.
So I guess if you are interested in visiting, probably submit to the CFP. It's open right now. I think it's open till the 14th of November. So if you have any questions about the conference, hit me up after the talk. All right. So let's get started. So I'm Anto Joseph. I work at Intel Corporation as a security engineer. I've been a speaker and trainer at these conferences. And I'm currently interested in doing some machine learning. I do some program analysis and mobile security mostly. And we are going to talk about symbolic execution, and which is basically, in a broad range, you could think of it as not really executing the program on bare metal, but then think of it as representing the program as a mathematical equation and trying to solve it. So that's symbolic execution. It doesn't require you to execute the program. Conclick execution is basically a technique that people have come up with, which basically includes symbolic execution with dynamic analysis. So it combines the best of both worlds. Why should we talk about this? So have you guys been to DEF CON or have you heard about the Cybergrand Challenge? All right. So it's basically a challenge by DARPA, which basically ask the researchers to come up with a system which is fully autonomous, which can generate automatic exploits and automatically find bugs in real-world systems or CTF binaries. And they were pretty good. And one of the teams actually open sourced their implementation. It's the Selfish team. And the tool that they have written is called Anger, so ANGR, and it's open source. So if you are someone who is trying to get started in reverse engineering or CTFs, maybe it's a good way to start with symbolic execution tools, because it helps you a lot when you want to get past that initial learning curve. Even if you don't know the reverse engineering like a professional, maybe the symbolic execution tools can help you to get you there. So that's why I'm talking about this. And it's a very active area of research. So we all know what a fuzzer is, right? It tries to generate input so that we could probably reach code paths and see if there is a vulnerability. Consider a typical fuzzer, which is a dumb fuzzer, which tries to mutate your input and tries to get into the vulnerability here. So let's assume that the vulnerability is over there, okay? And our fuzzer needs to get to this particular branch. Do you think a regular fuzzer would be able to hit that branch? It's a tricky situation, right? Because there is some sort of a magic comparison right here. So only if this variable is 1, 2, 3, 4, the vulnerability, the code vulnerable is executed. Then only it might trigger the crash. So when we are fuzzing, are we actually missing some of the important sections? Like, let's assume that we are fuzzing a file parser. The file has some sort of a magic, like the zip file has a magic, like 7-zip has 7-sed. If we mutate that part, the program is not gonna even load that particular file and try to parse it. So you need this sort of intelligence in your fuzzer so that it can reach or cover more code paths. Symbolic execution is a good way to solve such problems. So here, if we are symbolically executing this, the symbolic execution program will understand that it has to provide this particular argument A equal to 1, 2, 3, 4, so that it can get to the next path. Because it tries to represent this program as a mathematical equation. So A would become a variable, and it's a static assignment here. So it will directly be A equal to 1, 2, 3, and it will try to fill in other characters so that it can reach the vulnerable code point. So I'll have a demo of it later. Let me actually do the demo right now. So this is Z3, which is an SMT solver from Microsoft Research. Okay, so this bit, all right? Okay, maybe I'll increase the font size. Is this visible? Yeah, all right. Okay, so basically I just import Z3, I define 2 variables, and I want to find a solution which satisfies this specific condition, which is basically x plus y is greater than 5. And x is greater than 1, and y is greater than 1. So it's a very simple equation to solve right now. But when you represent binaries as a mathematical formula, it becomes really, really large. So you need to have a mathematical solver which is smart enough to handle that sort of formulas and try to simplify it before you actually process the formula. There are simplification passes before the solver actually solves the program. So we'll talk about it later. Now, let's do the thing. Okay. So this is a, okay. Right. Okay, it's a really simple C program, right? So it tries to get in some variables, and it tries to compare it to 0, which is greater than 0. So what are the possible outputs this C program can have? How many outputs does this C program can have? It's a really simple C program. Okay, why don't we find out? Right? So the first step in, so basically we are trying to use the CLI symbolic virtual machine. We will try to compile it to the LLVM bitcode and use the LLVM bitcode in CLI to generate test cases. So CLI is a symbolic virtual machine which lets you generate test cases if you have the source code for it. So right now I have the source code for the simple.c file, and I want to compile it with LLVM and you can just get LLVM from any tool chains. And you basically will end up with this particular file called symbol.bc, which is the bitcode file. It's not readable, it's just binary. And let's do that. Okay, so you use the CLang, which is the LLVM compiler for C programs, and you include this particular path, which is basically the header files for CLI, and you ask the compiler to emit bitcode for you. And it will be generated as this particular file, simple.bc. And now you run the CLI, which is the symbolic virtual machine, on it. Okay. That. Oh. Oh yes, I ran it on the C file. So you can see that the CLI symbolic virtual machine used the STP solver backend. So what is an STP solver? So, similar to SED3, STP is also a program which will try to solve the equation for you. Okay? And it has counted that it has executed over 30 instructions, and there are 3 code paths that were covered in this particular program. Okay? Now let's export this particular binary, and okay. CLI. Okay. So we basically compiled the file, and we have an a.out file now. And the test files will be in this directory, so they will be named as ktest. To run the test files, you can use something like .ktest onto the binary. Okay, and it executed, so we can check the return value. So the first return value is 0. Now let's execute the second one and check the return value, which is 1. And the third test, it's 255. So it executed all 3 branches of that binary without any human interaction. So on large scale programs, we want to have inputs that will exercise multiple parts of the binary. And we could possibly try to incorporate symbolic execution software into our fuzzers so that we can reach much better code paths. In fact, the Anger team has their own version of this fuzzer called the driller. So when it works in cooperation with AFL, so AFL has a status file where it reports how many favorite paths it yet has to explore. When it is running out, it takes a clue, the driller application takes clue from that particular file, and it tries to solve some of these paths which AFL can't find, and gives AFL more input so that AFL can go ahead and fuzz more and reach more code paths. So it's a really interesting paper about it, so definitely recommend to check that out. Now, let's understand how this works. So if you look at this diagram, this is basically how the program would be represented inside an SMT solver. So you give it an input, then you have a decision branch. Let's assume that we reach at a decision branch. Then it creates 2 different paths. So now the program has 2 different execution paths, especially around here. So it creates 2 paths, and when it goes further, it again creates a different path. So over here it will be a 3rd path, a 4th path, a 5th path, and 6th path, 7, 8, 9, 10. Around this program has like 10 different paths, or maybe have different combinations, like it could take this, and then it could take this, and then take something else. So it does this for every possible combination and generates input so that it reaches every single path. All right? And this is where you can grab CLI. It's an open source software. I use the Docker version of it. It's much easier to set up. You don't have to compile anything. It just works right out of the box, which is partially not true, because while I was setting this example like an hour ago, it didn't work. So I had to fix something. And this is how you could possibly run it when it works. So I will have the slides up so that you can just copy paste and get it done. I also have the example for how to run the Anger Docker container as well. I highly recommend it. Right. So this is what we basically did right now. We basically did compile a simple C program and generate outputs from it. Sorry, inputs for that particular program, which exercises all the branches. And how did the CLI program know that this is the specific variable that has to be made symbolic? So if you look at the source code, so I have a line here which says CLI make symbolic. So the argument A is made symbolic, and that variable is used to exercise this particular function. So that is why I know that that is how the symbolic execution software knows that it needs to track this particular variable's execution and generate input for this particular constraints. So these are the 3 arguments that function takes: the address of the variable, its size, and a random name which you can just use for tracking. And this is the tool, the CLI test tool is the tool that is used to exercise the test cases that is developed that has been generated using CLI. So it's a binary. You just give it the test case that has to be executed, and it just goes ahead and executes it. So let's look at a much more complex demo. Okay. Demo 2. Okay. Okay, that's quite something. Okay, so this is a C program which is printing a maze, and you have to find your way around this maze. So you could use the arrow keys ASWD, just like you would play a game, and you can reach the gate. So this is how the program is written. It's around like 100 lines of code maybe. So yes, you could audit the code and find bugs, but then I'm just lazy. I just want to use CLI to generate all the test cases and see if there is a bug. So how do I do that? Let me delete the files from the previous execution. So basically, you just go ahead and use LLVM to compile this particular C file. And you have to make some additions to the C file. So you need to reach the winning condition, right? So I have to make some changes over there. So you definitely don't want to reach the you lose condition. So you don't have to do anything about it. But I have to reach the you win condition. So I put a CLI assert statement here. So what CLI will try to do is it will try to execute paths which will result in execution of this assert statement. So you just put where you have to reach and then include the header file. So the header file is over here. Okay. And once you have done that to the source code, you basically compile it. So I will compile it now. Okay. Okay, so you basically use CLang again, and you ask CLang to emit LLVM bitcode, and just like the other example, you would run CLI on it, symbolize maze.bc, and it will try to execute this particular maze symbolically. It will take a while, and once that happens, you have to check if the CLI has been successful to reach an error condition, which basically is the result of the assert statement that we have put in earlier. So to do that, we'll basically type ls.last. So the latest test cases is always stored as a symbolic link to the directory CLI-last. So you can always use that. So it will refer to the latest execution. And you just print the error once. So I have an assert statement error here. So I am interested in seeing what exactly is that error. Or I'll basically replay it and see what is the error. One, 4, 3. Oh, sorry. Okay. Okay. Okay, so I have like around 4 cases which actually can reach the assert statement. So we could actually read the assert statements as such and find out what is the input. So I will exercise some of those inputs, and we can basically see how what is the vulnerability in that maze program. So it's so I have the program here, so I'll just try some random numbers just to make sure it works. Okay, that was, okay, so it works. Okay, so I have to use the different keys just so that I can navigate this maze over here. And let's try this input. Okay. So you see that it went right through the wall. So these kind of inputs, it's actually a bug in the C program. So these kind of bugs could be discovered from those assert statements. So those assert statements have what is the input that you need to provide so that you could reach this condition earlier. So they found that there are actually 4 practical inputs that one could provide to reach this condition. So I will try another input, which is a much smaller input than the recommended solution. So you see it is just going right through the wall. There you go. So you could go ahead and audit the C program, or you can just generate test cases and see what are the failed assert statements. And I have 2 more of those. So feel free to like execute this and have some fun. So yes, it's all good when you have this program source code. So what do we do when you don't have the program source code? That's going to be a much more real-world CTF approach, right? So I have tried to like solve one of such programs. So let's assume that we have the demo tree working. Okay, so stage2.bin, it takes in a password. It just gives you a try again if you are unsuccessful. So I need to figure out a way to get symbolic execution tools like CLI to work on it. So I definitely need the source code. So I go to the next best thing, which is usually an IDA disassembler. So, so I loaded the program over here. The main function is over here. It looks like this. And you have to reach you have to reach, you definitely don't want to be here. Okay? So let's just try again. So you have to ignore that branch. And one of the features with IDA is you can use this plugin called Hextrace, which basically make the code into sort of C. So it would look something like this. It looks like pretty compilable code. So you might have to like tinker around a little bit. So I did that. And yeah, so it's just basically adding the devs file from the IDA's plugins directory. So all these are like write-ups that are publicly available so that one can learn how to use IDA or, Anger or CLI. So you can always look it up. So you include the devs file here. You basically need CLI so that you can have the assert statement to work. A regular C program right here. And good. So I need to reach good. So I put in a CLI assert statement here. And let's try to compile it. Okay, so do this. And now we have the bitcode file, which is this. Now, we know that the argument to this program is what needs to be symbolized. So earlier in the first program, I kind of symbolized the variable A. Here, it's a command line argument. So I am symbolizing that. And it ran some test cases, which was like super quick. Okay. And let's see what are the errors. Okay. So we have one of those test cases here. So let's use the K-test tool to see what is the output. And it looks like, yeah. So you can see that argument has been symbolized right here. So sim_args is basically what is being symbolized. And one of the things about CLI is that it basically stops when you reach the first particular assert statement. So if you want to find out all the possible outputs that the program can have, you have to give it another argument. So basically the graph looks like this, and this is the C program. And let's okay. To 9. Yes, and we have the key here. So I just tried to print the wrong test case, which was a mistake, but we have the key in the right file. So it's called Pandy Panda. So let's try that out. Okay, stage2.bin, and yes, it works. So it printed the key right there. So I didn't even know what the program does, but then I solved a CTF. So do you think this is cool? If this is cool, if this is not cool, what is? Yeah. So this is the easiest way for someone to like get started with binaries. Like you don't necessarily need to know what. You just need the basic understanding of looking at a graph and basically telling that I need to be there. That's all you need. So probably one can do that. I think everyone over here can do that. All right. So what else can we? All right. Okay. So what's even more cooler? Can we do this all inside IDA? I don't want to like just move virtual machines and stuff like that. So can I just load a binary inside IDA and just tell it that I just need to be here? Can IDA do it for me? I guess it can. So let's, okay, I'm not sure this will work, but give it a try. Okay, so I'll open a crackme file, which is an exe file, Windows 1, and it passes everything for me. And this is how the function looks right now. So you lose or you win. So I just need to be at the win condition. So what do I do about it? Let's, first of all, try to run the binary with some arguments. So this is how the binary looks like. So, and you basically give it something and it just prints loose. Okay. Okay, so go here. This is the graph. I need to be at the win condition, so I select the local Win32 debugger because it's a Windows binary. I give it an argument. So you just go to process options, give it some A's or something. Give it OK. Just to make sure that it runs. Okay, it runs and it exits. So now we need to trace this. So the plugin that I'm talking about is called Pounce. It won the IDA plugin contest last year, I think. So it's a really cool plugin. And I loaded it. And I need to show, this is the config file, the config menu of Pounce. So you basically select the symbolic engine, and I just want to track the argv, which is basically what you give as the argument to a binary. And click OK. Now run the debugger again. And if you see right now, there is a lot of execution that's happening right here. So Triton is another symbolic execution framework, which is really good at this. So the module developers actually use Triton to solve this particular program over here. So let's look at what has happened to the graph, the IDA graph. Okay, so you can see that the graph has been colorized. Okay, right, and the function has been renamed. So whatever has been tainted by the user argument will be colorized so that it's easier for you to notice. So it basically says that these registers have been tainted with the input. This memory has been tainted by the specific input, and this is the jump that one has to take. If you can take that particular jump, you can get to the win condition, but then you don't know what is the input that you have to give to this binary to take that jump. So you basically right-click on it, use SMT, solve formula, click on it, and it prints you the solution right here. Is that cool? Definitely, right? Thank you. So just to verify that the solution works, yeah, you win. All right. So did I do any reverse engineering? No, definitely not. So all you need to do, right now it's a really simple program. It's much easier. So if you do it on large binaries, it takes a consistent amount of time. But I would recommend not to run it on the whole binary as such, but then the branches that you just want to take. So let's assume that you are somewhere in the binary, and you just need to figure out how to get this particular branch. So you load the symbolic machine from that specific instance. You don't load it from the entire start of the binary. So you just load it from that specific instance of that binary. So let's assume that there is some sort of a compression, and after that there is a password check. So you can skip the compression and just start the symbolic execution right before the password check. So you kind of makes things simple for the symbolic execution engine so that it solves in very less time. So if you just do the whole binary, there's a problem called the path explosion, because modern binaries can have multiple paths, and to solve all that paths, it's not going to be done in linear time. It's going to take forever. So some of the DEF CON challenges that we have the write-up for in the Anger GitHub repo takes around 8 minutes or 10 minutes, and those are the simplest of the challenges that you get the idea, right? So yeah, in 8 minutes you can actually get the key. That's really cool. But then if you simplify it just to that specific logic, it will execute much faster. So that's one thing, and I have 3 more minutes, right? Okay. So I will do another demo of, so right now all of this required some sort of a source code. Now I will do it without the source code. So that's going to be like the final demo. Let's hope it works. And okay, I can safely close this. Okay. Right. Right. So this is binary IS3 crack me. So I need to enter the secret key to just go in. So I just enter something. No. So I don't have the source code for this. So what can I figure out about this specific binary? So let's use Reda2 just easier. Demo 1. Is this visible? Maybe a little more big. Okay. Yeah. So I use Reda2. You can use IDA or whatever you like. Just do a basic analysis. I look at this, and I need to print out the main function, go to it, print out the graph, and the graph looks like this. All right. So correct. That's the secret key. This is where I need to be at. So note down this offset. Okay. Note down the offset where I need to be, and okay, just to make sure I have the offset. Okay, when I enlarge, the graph is screwed up. Okay, better. All right, 400602. Okay, that's where I need to be at. I don't have the source code. I just have this offset. So what do we do? Let's take a Python file, sol.py, and this is just the Anger constraint. So you basically create a project. Everything in Anger is a project. You just give it the binary name. You basically state that the argument is what you need to be symbolized. I don't know the length, so give it like 100 bytes. And I need to figure out, so I am basically asking Anger very politely, just find me this particular offset, okay, for 00602, right? And let's see if it works. So, okay. I need to be the Anger guy. And, okay, moment of truth. Any moment now. Okay, yeah, here you go. So it basically executed and it solved the CTF for me. That's the key. Just to verify, I'll run this key through. That's the secret key. So did I do anything? Again, I just know the offset where I need to be at. You just ask Anger, and it does the hard work for you. So I highly recommend this tool for you. I think I should do some slides now. Right. Okay, quick. Okay, we'll just rush through the slides now. Basically, so this was the. So this is just what you could use for CLI to symbolize whatever you like. I will have the slides up so you can take a look at it. So path explosion, as I discussed, is a problem. So you have to be very specific on what you need to solve. Code obfuscation. So regular code obfuscation is not really considered as a countermeasure because the SMT solvers can remove that code. So if your code is not going to work on the input, it's just going to just ignore that code. So if you just add jargon to the program so that you can make it tougher for a reverse engineer, that's not going to work for the symbolic execution engine. So you need to have something that works on the actual input and do something meaningful, and then only that sort of obfuscation will be of any use. And this is basically about anger. It's freely available. Again, I recommend use the Docker container. If you have any doubts about anger, the Slack channel is very helpful. So since it's a community project, it can break sometimes. So if you have a doubt, just hop into the Slack channel. There are many people over there, so which has basically helped me to work on anger. So I highly recommend it. And these are basically the components of anger. And I did that. And the pounds was the IDA plugin that I used to solve the program within IDA. And thank you.
Okay, thanks a lot, Anto.
Yeah. So I basically ran out of time, so I'll take questions. I'll be around. So
Okay.
thank you so much.
Thanks a lot.
And thank you for having me.